I had to cut quite a bit from the talk, but hopefully it'll be a closed presentation in order to get everybody to lunch on time. So my name's John, and I'm going to be speaking about Ringin the Water Bell. It's a project that I worked on in the context of my postdoc, advised by Jay and Iran here at the Hebrew University, with a lot of support and theory development from Hillel Aharoni, who you'll hear from later today. And I want to thank the organizers for putting together such a nice meeting. It's really an honor to speak with such an audience, including Jay, of course. But I want to point out that for the first several weeks when I started working with Jay, he was telling me it was his 49th birthday. So I think there might have been a clerical error in the date of the date of birth for Jay for the conference. But first, a little story about something I learned about Jay in the context of doing the postdoc and living here. So I moved to Jerusalem after living in Rehovot for a while and commuting, and I needed a bed. And this came about because I had rented an apartment. I had the mattress, but I didn't have a bed. So I came in, we had coffee in the morning as we typically do. And basically, Jay, I'm going back and forth. I'm saying, where can I get a bed? And Jay says, well, I have an extra one in the basement that I'm not using right now, so why don't you come over and we'll put it in the back of the SUV. No problem. We'll move it over to your apartment. No issue. So we haul the bed frame upstairs from several flights of stairs from the basement, and we try to fit it into the back of the SUV, and there's no way we're getting it in. So we tried every single orientation, impossible, and this was after having ignored Iran's advice and taking his pickup truck to move the bed frame. So I was stuck there with my Citroen Saxo, which is a very tiny car. I don't know if you've ever seen one like this. I've driven more powerful motorcycles, as a matter of fact. And so with the car, I had recently moved a mattress for a friend of mine, and I had the rope in the back. So we tied the bed frame on top of the car, and it was very secure. There was absolutely no way it was going to shift. We made one error, and we realized that when we went to open the doors. Basically, we had tied the bed frame on through the windows, and I've entitled this slide, Jay Does Yoga for a reason. So I like wedged myself through this tiny window in a tiny car, and Jay gets into this yoga stance that was just the most impressive thing I've ever seen, and essentially miraculously floated through the window frame. It was incredible. And at that stage, I knew that Jay does miracles not just inside of the lab, but also outside. But okay, so we're here to talk about the geometry and physics of fluid sheets, which Emmanuel has introduced so nicely with the talk prior. And he's done a ton of work in the area. You'll see constant references to his work throughout the presentation. But basically, the motivation to look at the problem came from just images like this, where you have a fluid sheet. This one, for example, is formed by splashing of a liquid drop on a solid substrate. And you can see that there's a lot of really interesting dynamics and physics going on here. From, for example, just the shape of the sheet at the cusp here, to the rupture of the sheet through instabilities that Emmanuel has studied thoroughly. And it's not just coming up in kind of idiosyncratic physics problems, but it's also very relevant for sprinkler systems. It turns out, and Emmanuel can tell you a lot of details about how you can basically distribute small volumes of fluid over large volume areas by undergoing by triggering an instability of the fluid sheet. So this is a very rich system. It's full of instabilities, and that was one of the things that motivated us to look at the problem when I first came to work with Jay and Iran. And so this is one of our first experiments in Iran's sink. So we have basically a laminar faucet jet impinging upon a spoon, and the liquid is spreading out and separating from the spoon's edge into a sheet here. Okay? So this structure is relatively stationary. So the fluid is flowing through these curves, and that turns out to be a really important part of the problem. And so essentially we have two different key parameters in the problem for the system that we're going to look at. The first is the kinetic energy of the fluid. So imagine that you have basically the fluid sheet here, and the fluid flowing along these arrows like this. It's being redirected. And using like an undergraduate control volume analysis, you understand that there has to be some force acting on the fluid in order to redirect it, right? And so there's a kinetic energy associated with the change of direction of the fluid when it's flowing through a shape like this, because there is some external momentum being imparted in the fluid to change its direction. And the kinetic energy scale associated with that is given by the inertia of the fluid times characteristic volume. And so that's actually being driven by surface tension in this case. So for surface tension, basically you get energy by forming additional surface. And so here I have a paperclip floating upon a liquid bath, and the way that the surface of the bath is able to support that paperclip is by curving, creating additional area, and essentially lifting it off or keeping it from sinking into the bath. And the energy associated with that would be the surface tension coefficient times the additional area that you've generated by curving the surface squared. And it's the ratio of these two. This is a parameter that came up a lot in Emmanuel's talk. It's the Weber number. So the Weber number is basically an expression relating the proportion of kinetic energy in your system to surface tension energy in your system. And that's a key parameter when you're looking at a water bell. And this is the system that we're going to look at in order to study driven fluid sheets. So here, if you calculate the Weber number based on the jet's diameter, it's of order a couple of hundred. And so we have a liquid jet impinging on a target, and I'm going to go into detail about how we make that target in just a moment. But I want to point out that these things are intrinsically stable for sufficiently low values of the Weber number. And that's as opposed to the Rayleigh plateau instability, which will trigger an intrinsic instability in a cylindrical jet. And one of the nice ways, I think, to kind of understand why the sheet should be stable is that whenever you perturb the thickness of the sheet, so let's say you had a sheet at first and you made it get thicker in certain regions and thinner in other regions, the thicker regions are going to have higher pressure, the thinner regions are going to have lower pressure, driving a flow in order to sort of equilibrate it and keep the sheet flat. So again, one of the things that I want to point out is that as long as the jet Weber number is less than about 500, we're going to avoid a shearing instability, and the sheet will be intrinsically stable. So in order to study the dynamics of fluid sheets, we're going to drive the fluid system. And the way that we're going to do that is we have a target system as follows. So we have our fluid jet impinging upon a central cylinder. And we put a collar around the cylinder. This was inspired by Christophe Clanet. And essentially by changing the offset of the two components of the target, we can actually control the separation angle that the sheet will separate with. Okay, so we can do that both statically and dynamically. One of the key components of this type of setup is that the separation angle will vary linearly with the separation distance between the two components of this target. So this results in a steady state water bell. Again, we're going to be working in a parameter regime where the water bell is intrinsically stable. And at steady state, the solution of the water bell comes from just balancing your surface tension term and the acceleration. So this is all basically F equals ma. And you can look at this as basically surface tension balancing centripetal acceleration because the fluid is being accelerated through this curve. And one of the things that jumps out immediately after you look at this expression is that you have an intrinsic length scale, which is given by the mass flux rate normalized by the surface tension. This length scale is a key parameter because it's going to tell you how large your water bell will be. So depending on your separation angle, your water bell will be larger or smaller depending on how large this length scale L is. And so here we're basically forming a steady state water bell by balancing surface tension and centripetal acceleration. The fluid velocity is constant and tangent in the fluid sheets. And what that means is that as you get further out, the sheet will be thinner by mass conservation. So you start with a plug of fluid that has the cross-section of your jet, and all of that is going to be conserved at a constant velocity out here. So the sheet thickness has to be smaller in order to maintain a constant fluid flux. And essentially, there are two key parameters that we see from this balance. One is the length scale, and the other is the separation angle. So okay, so now we can do this sort of dynamically, and what I'm showing you here is what happens when you pull the inner component of the target up relative to the outer component. You can go from a flat sheet to a steeper sheet. And what we're going to do is we're going to fix one value of this offset and perturb around it with small driving of the offset distance between the two components of the target. And basically that's going to allow us to study the response of the fluid sheet. So here I'm showing you a dramatic example of what happens when you drive the sheet at about 50 hertz here. And the flow rate is of order several meters per second. And basically we see that there's quite a bit going on here. You have this dramatic feature that's propagating through the sheet, and then it's going to rupture into smaller filaments through this instability cascade that Emmanuel has studied in detail. And
how much do you modulate then?
okay, so a typical offset distance to make the sheet go from flat all the way to relatively closed would be about 100 microns.
Oh,
Okay? But in that case, we're probably modulating with a modulation amplitude of 40 microns or so. And most of the stuff that I'm going to focus on here is when we go to the extreme of very low amplitude modulations of the target. So basically, that's what you see when you drive the water bell with the modulation amplitude of about 10 microns or so. And so you get these features that are going to form on the outer edge of the bell. And in order to sort of begin getting a grip on what we can analyze here, we have to make measurements, of course, of this profile. So what we're going to do is we're going to go and take the time average profile or the profile before we start forcing, they're equivalent in this case, and then we're going to measure the instantaneous distance normal to that surface in order to measure the amplitude as a function of a spatial coordinate, right? So when we do this as a function of arc length, for instance, we can then extract the deviation from that background shape and plot it as a function of the arc length coordinate. So this is just for one time snapshot, but when we take a time series of snapshots and we look at it, what we see is that we have sort of a propagating disturbance that's coming through the water bell here. So these are equally spaced in time, and if you just follow the peak, you see that it's moving forward, and this is one complete cycle with 5 different snapshots in it. And so we have traveling waves that are propagating down the bell. And then if we look at the amplitude envelope, for instance, we see that it's actually modulated in a significant way. And so basically the amplitude of the disturbance is varying non-monotonically with the position, okay? And so this is for a moderate forcing amplitude. And one of the key questions that we came about when we tried to analyze a lot of these, we had a theory to compare against, but we realized that there wasn't an a priori way for us to get the amplitude out of it. And so what we wanted to do was go after understanding what sets the amplitude of the response of the water bell. So here, what we've identified is this nodal structure, but this has already been explained in 2006 for the flat case in the Bremond paper that Emmanuel mentioned earlier. And we've extended that to an arbitrary geometry in our recent paper in Physical Review Fluids. But now I'm going to go, as I said, we tried to explain the amplitude response from first principles, and we were not able to do it initially. So essentially what we did is we went down to lower and lower forcings in order to make sure that the forcing was truly perturbative. And I want to point out that the amplitude scale that we're looking at here is really, really small. This is 30 micron amplitude response on the water bell surface, and we get that by oversampling in time. And so what I'm going to show you is several different profiles. So these are now the amplitude envelopes. They're not instantaneous. I'm going to show you several different profiles where we're incrementally increasing the forcing amplitude. And so we take one step and we see a certain amplitude here. Step 2, step 3, we see a minor increase in the amplitude of the response. And then step 4, everything starts to kind of blow up. And ultimately, we see that the amplitude is growing very, very rapidly in comparison to how it was growing initially, with the lowest forcing amplitudes. And so we see that for a very small forcing amplitude, we have basically a characteristic profile that we're measuring. And again, we're using sub-pixel resolution to get to extremely small amplitudes. And we had to do this because we were not able to explain the amplitude of the bell from first principles at the intermediate amplitudes we were forcing at most of the time. Yes?
I'm sure you said this, but what are you changing between those curves?
So remember the offset distance between the two components of the target? That's what we're modulating when we're driving this this system, okay?
Okay.
No. So we're basically modulating that periodically, right? We're driving it about a couple hundred hertz, and we're changing the amplitude of that modulation.
But that's not the amplitude that's being shown.
No, indeed. So this is the amplitude of the response of the bell, right? So there's the forcing amplitude, which is in the target. We're controlling that completely. We have a prescribed frequency, prescribed amplitude. And this is the amplitude that we measure along the bell and in the envelope of the response. Okay?
How effectively axisymmetric is your bell? It is very axisymmetric.
Yes, it's very axisymmetric. Yes. The question was how axisymmetric is the bell, and the answer is very. So basically, then we talked to Hillel because we realized that we had a puzzle on our hands. And Hillel, of course, is a brilliant theorist, and he was able to put together a model for the system. So basically, again, we have the same effective equation, except instead of being at steady state, where the shape that the fluid is accelerating through is stationary, Now we're going to allow that to vary, right? Because we have these propagating features that are moving down the water bell. So we need to have some convective derivative, which we have here, and that introduces a nonlinearity into the equations. So basically, the two contributions from geometry principally come from surface tension again. So we have the two different curvatures here and the mean curvature. And then there's also the acceleration term, and this is now unsteady acceleration. And I want to point out here that there's a wave-like character, because essentially we have two time derivatives, two spatial derivatives, and if you actually take the ratio of these two coefficients, you end up with what's called the Taylor-Kulik velocity, which in short is what happens if you have like a thin film suspended on wires and you pop it. That's the velocity that the hole will open with, okay? And that depends on the thickness of the film very sensitively. But that's the velocity, the characteristic velocity that's coming out in this balance here. So we're going to go ahead and solve this in the steady state, which is a well-known solution. It's been calculated before, going all the way back to Savart, I think. And we're going to perturb the steady solution. So basically, we're going to introduce a spatial and temporal perturbation to the steady state solution, and then we're going to basically substitute that into our dynamics, and we obtain the following linearized equation. We can transform that and solve for k. So this is basically the phase that these two modes are going to propagate with, right? Because when we apply a perturbation at the target, we're going to get one mode that's going to move faster than the fluid velocity and one mode that's going to move slower than the fluid velocity. And that's captured by the plus or minus features in the expression for the phase. And I want to point out that we understand exactly what's going on here because we can measure essentially every single parameter or control every single parameter in this expression, right? And and I also want to point out that K has has imaginary solutions, so that is basically telling us that we should have some geometry-dependent growth or decay of the water bell's response when we drive it. So then we can integrate that phase in order to solve for the growth or decay of the response. And again, we're going to take our steady-state water bell shape and integrate that expression for the phase down the water bell. What we see is that we have a strongly negative imaginary component for our slow-moving mode here. So that means that one's going to grow in response, and the fast-moving mode is going to decay in response. And so this is basically what we would predict for the growth using our theory for this bell shape. And I want to remind you that the growth that we have here is going to be very dependent on the geometry of the background of the bell, right? So the question is that actually what's going on here? And it turns out that when we compare against our the theory against our experimental data, we find reasonable agreement. So essentially we have the amplitude response, which we've measured, plotted in red here, and the amplitude response predicted from our theory for this particular configuration with a very sharp separation angle driven at 80 hertz. We can do that, of course, for arbitrary separation angles and arbitrary frequencies, and we get reasonable agreement in all cases. And again, these are very, very small amplitudes that we've measured here. They're down to where we had to go into sub-pixel resolution in order to measure the response of the bell. So essentially, we've seen this growth occurring for very small forcing amplitudes, but then the question becomes what happens when you go to larger forcing amplitudes? So essentially, again, as we incrementally increase the forcing that we're applying, the amplitude of the forcing that we're applying, we see suddenly that things begin to break away past a certain value, right? So in order to characterize this response, what we do is we're going to measure the amplitude of the response at a fixed arc length coordinate s. And this is essentially what we see when we do that. So we have a very subtle increase for the first increases in the forcing amplitude. And then as we continue to increase, we see a sudden takeoff of that of the response of the water bell. And then up here, we recover sort of a linear response. And this is the response that's been measured and characterized in prior experiments. And keep in mind, it's still quite small. So we're only at like 100 microns response amplitude here, right? So again, initially we have a linear increase in this lower area here, and then we have a. But then there's the question: how do we describe this nonlinear character of the water bell's response? And the dynamics are going to suggest it for us. So basically, we have a critical forcing amplitude, and then we see that the response is going to grow rapidly with the forcing amplitude. until growing linear again with the forcing with a larger slope. So in the nonlinear regime, we actually see linear response of the bell. Okay? So this was something that was quite puzzling for us for quite a while. But then we thought about it a bit, and we realized that it has to be basically an instance of a transcritical bifurcation. So essentially, beyond this critical forcing amplitude, what we see is that the growth, or we should have the normal form with a quadratic saturation. And this is a key element of this phenomenological description of the dynamics, because it allows us to get this linear response in the larger forcing regime that we see. And here our dimensionless parameter is going to be distance from the critical forcing that we're applying. So another point that I want to make is that T and S are not truly separated here, because the features that we're sort of initiating by perturbing the water bell can grow as they go downstream, but everything I'm showing you here is at a fixed value of the arc length coordinate S. And so this particular normal form has an analytical solution, and it depends on the applied amplitude of the forcing, and the saturation goes linearly with the forcing, or sorry, the forcing parameter epsilon. And so basically, when we plot this theoretical description, just matching a couple of the parameters in the problem, we get reasonable agreement with the nonlinear response of the water bell with a phenomenological description. And essentially, one of the things that we felt was compelling in this case for these dynamics with the observed response is that the linear amplitude response that comes from the quadratic saturation term is emerging from a broken up-down symmetry, right? So that comes about because we have a directionality where we've applied the momentum from the jet into the target, and that has biased the system. Okay, so basically we have predictions and experimental data that show good agreement for the smallest forcing.
How the system knows about this breaking of symmetry?
There's momentum in the water, so when it's coming through at the target.
Did you check sort of the term if it's really negligible?
Sorry, which term?
Sort of the term.
The third order term.
Sort of. Ace cubed in energy integration.
I didn't, no. But I mean, the fact that we see the linear increase here, and it extends beyond the range of this plot. It continues to go linearly beyond that. So I mean, we would have seen the third order term come about in the experimental data, I think, if it were pertinent.
Your pairs are always open.
Yes, yes. So
Have you tried to close them?
no, we haven't. That introduces a different equation, because then you have to take into account the air pressure inside of the bell, or you can use a straw or something like that to give you free access. But there are a variety of instabilities that come about there. Actually, Christophe Clanet has done some very nice work showing that system in and of itself is unstable and will undergo cyclic response. Okay, so basically back to the summary. So we have predictions of the experimental data showing good agreement with the theoretical description that Hillel put together. We have the response saturating at a critical value via transcritical bifurcation. And this is something that I didn't get to get into because of time, but basically we were also able to look at the structure of the nodes, the location of the nodes, and we were able to explain that quite nicely. And I recommend, if you're interested, to look at the article that we recently published in Physical Review Fluids for details there. And I want to emphasize that we've identified the growth regime with experiments that was predicted by Taylor in 1959. And I also, of course, want to thank and wish a happy birthday, a very happy birthday to Jay, Hillel, and Iran, who were all key in helping this project happen. So thank you.
Theorist question. If you
Sure.
go back to the graph, yeah.
Yes.
The purple point is the only. If you didn't have the purple point, I would buy yours.
Okay.
I'd be happy.
Yes.
So why does that purple point not bother you?
It doesn't bother me because basically we have two parameters that we can modulate with the model, right? And as a matter of fact, really, if you wanted to talk about this A here, it's not the literal A of the response that we're measuring, but rather it's the distance from the linear solution, right? So, I mean, basically there are a couple things there where if we wanted to tune them like precisely, we could probably get a slightly better passage through this point.
You should add field, and then you can get much better field. additional constant part on the right-hand side.
I don't even think we need to add any.
Then it better fits this point.
Okay. Okay. Okay.
Because it's
So add a field.
roll up earlier.
I see.
Constant.
A constant. Okay. Okay.
That's here.
So
That's usually non-idealities if you don't know.
right.
So, there's air both outside and inside.
Yes.
You didn't say much about that.
No, indeed, we ignored it completely, and so one of the things that I said quite early on is that we are stable to the shearing instability, the Kelvin-Helmholtz instability, right? So when you go beyond a certain jet Weber number of about 500 or so, you start to see flapping that's excited through shear with the air, which Emmanuel has investigated in detail. But for us, basically, we worked in a regime where our sheet is essentially stable to that instability. And as a consequence, we've ignored the air. Now, there could be maybe some contribution from pressure, right? Because we have these disturbances that are pushing the air back and forth harmonically. But that would, I think, manifest itself through the Kelvin-Helmholtz. So
And I guess there's a vortex ring inside.
could be. I mean, but again, that's going to be coupling through shear with the air, which I think the effect of the shear with the air is well established when you go to a higher jet Weber number. Yeah. Yo, hi. So I showed you the one example where we go to 50 hertz, right? And that was really dramatic and yeah, it was a lot more dramatic than what we saw with the 200 hertz. I mean, essentially, we were able to show the linear response with lower forcing frequencies, like at 80 hertz. At 5 hertz, we didn't make measurements, and I think that there are other instabilities that can kick in. Yeah, so basically, I think Hillel's calculation is relevant in the high frequency limit, and that's exactly why we worked with the frequencies that we worked with. And if you go below that high frequency limit, then the model is not describing those dynamics, and it's a different situation. Yeah.
Okay, if there are no further important questions, then let's thank all the